record this, and tomorrow morning I'll send you a link as to how to watch this recorded session in case you want to review it.
Okay.
And I got these two images that you sent me.
Mm-hmm.
Okay. Where would you like to start tonight?
I think we could probably start at number 5.
Okay. You're good with 1 through 4?
Yeah, I understand how to do this.
Okay. So, let's look at the graph on 5. Can you see where there's a vertical asymptote?
Yeah, it looks like there's one at -3.
Okay. So, can't be A,
True.
can't be E, because this would have a vertical asymptote at 3. So it's got to be either C or D, right?
Yes.
Both of them have been moved up 2 units, which the graph has been moved up 2 units. The only difference between C and D is this negative sign. So in one case, we have a hyperbolic function. If I were to graph C and put my vertical asymptote in there and my horizontal shift, this is the grid that I'm dealing with. And I'm plotting a hyperbolic function. Well, all hyperbolic functions tend to look like this. Okay?
Okay.
Or, if they're negative, then they would be in the 2nd and 4th quadrant instead of the 1st and 3rd quadrant. You know what I mean by the quadrant?
Yeah.
In other words, this whole area right there is quadrant 1. This is quadrant 2, quadrant 3, so forth and so on. Much easier to erase online than it is in person on paper.
Yeah, fair enough.
So, how do I know whether this curve is the positive hyperbolic function, this one here, or the negative one over here? Well, the best way is to plug in a number for x and see what value you get. Okay? In other words, that'll tell you which function we're dealing with here. Because we don't know at this point, but what we do know is that we're looking at a curve that looks like it's 2nd and 4th. So almost certainly we're dealing with the negative. Because the standard hyperbolic function, which is y equals 1 over x, that's in 1st and 3rd. If I want y equals minus 1 over x, that's in 2nd and 4th. So almost certainly this is the negative one. But let's plug in a number. Let's write down this function and plug in a number just to be sure that we're dealing with the negative function. So we think it's this function right here.
Okay.
Let's prove it. Let's make sure that that function is this curve. So pick a number for x.
Alright, 2.
Okay. So when x is 2, y is minus 1/5 plus 2, right?
Yeah.
Which is 9/5, a number less than 2. Well,
Okay.
if I go to 2 on my curve here, I'm at a number less than 2. I'm in the right spot.
Okay.
So the fact that I'm still less than 2 when I go to 2 on my x-axis means I am in the correct quadrant here. We are in the second and fourth quadrants, because otherwise I would be above my horizontal asymptote. In other words, if I use the plus answer C, and now I plug in 2, I get 11/5 for y, right?
Yeah.
Because it becomes plus 1/5 plus 2. So that would be a number greater than 2. And yet I can see that for this to be greater than 2, it would have to be in the first and third quadrants. So you can always just plug in a number and see which quadrant you're in to determine whether you have the right graph or not.
Okay.
Okay? All right. Let's look at 6. Now, with the e to the x function, that's a great function for illustrating both minus f of x and f of minus x. Okay? What's the difference between minus f of x and f of minus x, regardless of the function? What does this minus sign do?
We learned this, I can't remember.
It's a reflection over the x-axis.
And isn't the other one reflection over y?
Yeah. So
Okay.
if my f of x is just e to the x, that's my elementary function.
Okay.
Well, e to the x looks like this. Okay? So if I said negative e to the x, that's negative f of x. This corresponds to this.
Okay.
So I would reflect it over the x-axis and it would look like that.
Okay.
But if I said, well, what is f of minus x? What is f of minus x? If f of x is e to the x, what is f of minus x?
Negative e to the x?
No, that's minus f of x. Let's review this, because this is a real important point in mathematics. If I said f of x is equal to x squared plus 1, what is f of 2 equal to?
5.
Okay, so you know that whatever is in the parentheses gets substituted for x, right? That's what you did. You substituted 2 for x. Well, what is this equal to?
It would be x squared.
Well, first of all, you just substitute x minus 1 for x.
Okay.
In other words, no matter what is in the parentheses, whether it's a number or a variable, you substitute it back into the original function. Okay, that's real important to understand. So, what have I said? What is f of minus x here?
It would be negative x squared plus 1.
Negative x in parentheses squared plus 1. which turns out to be the same thing as x squared plus 1. In other words, this is an even function, so that f of minus x is the same as f of x. Okay? But if my original function is e to the x, and I am looking at a function that now says e to the x minus 2, how would I get that? What would that, that would have to be f of x minus 2, right?
Yeah.
Okay. And minus 1 would be f of x minus 2 minus 1. Would be e to the x minus 2 minus 1. Well, when you do this kind of thing, what are you doing? That's a horizontal what?
Oh,
So
horizontal shift.
to which direction?
2 to the right.
Okay, good. And the minus 1 is what?
A shift 1 down.
Okay. So I'm going to take my standard e to the x curve. And what is this point right there?
1, 0,
0,
1.
comma 1. And I'm going to move that point, because that at this point is the only point I know that's on the curve. I'm going to move it 2 units to the right and 1 unit down. So that this point, in other words, do I have a horizontal asymptote here? In my original, in the e to the x function, do you have a horizontal asymptote?
Yes.
Where?
Or no?
Yes.
Is it at 0?
Yes, it's y equals 0. So this minus 1 moves that horizontal asymptote down 1.
Okay.
So now I want to draw my e to the x function based on this horizontal asymptote. It wouldn't go through this point, it would go through this point.
Right.
Now I got to move that 2 units to the right also. So let's make this point right there. This function, e to the x minus 2 minus 1, has to go through that point. I'll draw it in blue. It's got to look like this.
Okay, so that would be C. That makes sense.
Yeah, C is the only, well, yeah, you're right. It's got to be C. This one has been moved down by 1. This one has been moved down by a lot more than 1. This one has been moved down by a lot more than 1, merely because you can see there's a point here that's below 2. So it looks like these two maybe had their asymptotes moved down by 3, this one and this one. This one has been moved down by 1, but has been shifted to the left, not the right.
Right.
And as far as shifts go, remember that it's always x minus h for most anything you're talking about. Whether you're talking about a horizontal translation, a positive h means shift to the right.
Okay.
And it doesn't matter whether you're talking e to the x, or if I'm dealing with the function y equal x squared, what would this look like?
That would be a parabola shifted over 2 to the right from 0, so it would hit 2 at the...
Exactly. So the trick here is to be able to look at that, and the f of x notation works so much better than the y does here.
Okay.
And I'll show you why. Because I need to figure out what this is in terms of f of x notation. Well, what would that be? That would be f of x minus 2, right?
Yeah.
Well, this tells me horizontal translation 2 units to the right. So if you can take the function and put it back into this type notation, well, you only have a certain number of things that you can do. You can do c times f of x. That's a vertical stretch. You can do f of some number times x. That's a horizontal stretch. You can do f of x minus c. That's a horizontal shift. You can do f of x plus c. That's a vertical shift. That's pretty much it. The only other two things you can do is minus f of x, reflect over x, or you can do f of minus x, reflect over y.
Okay.
So I think you can see that the f of x notation works a lot better than y does here.
Yeah.
It allows you to take a function and figure out which of these 6 things that it is. In other words, even though they gave you y equals e to the x minus 2 minus 1, you need to be able to see that that is f of x minus 2 minus 1. In other words, that is a combination of that and that.
Okay.
And the e to the x is a better function than y equal x squared to demonstrate that, because each of these 6 things looks different on e to the x. Whereas if I was using y equal x squared to demonstrate this, these 2 things look the same. The reflection over the reflection over the y-axis looks exactly the same as f of x. There's no difference if you're talking the parabola y equal x squared. But if you're talking the e to the x function, this looks different than f of x.
Right.
All right. Let's look at 7. So they're taking this function, f of x. We don't even know what it is. We don't know if it's a parabola or if it's e to the x or any of that. We just know it's some function. And they're stretching it by a factor of 3. They're compressing it horizontally by a factor of 2. And they're shifting it vertically down by 2. Okay. So if the point 2 comma minus 3 is on the original function, well, if I did just this, in other words, if I had f of x minus 2, then the point 2 comma minus 5 would be on my new function, right?
Yeah.
Okay. So I'm not only shifting it down by 2, but I'm multiplying it by 3. What would 3 f of x, what point would be, if x was 2, what would 3 f of x be? Based on the fact that this point here is on our curve.
It would be 5.
It would be 3 times minus 3.
Oh.
In other words, remember what this 3 does. It stretches whatever the value of y was by a factor of 3. Well, in this function here, when I get to 2 on the x-coordinate, I'm at minus 3 on the y-coordinate. So if I said, well, what does this do? What does 3 f of x do? Well, that means that instead of 2 minus 3, the point would be 2 comma minus 9, right?
Yeah.
Okay. So if I said 3 f of x minus 2, then the point would be 2 comma minus 11, right?
Yeah.
So if I say 3, well, let's go back and take the simple case. To figure out what f of 2x would mean. F of 2x would mean the point would have to be 4 comma minus 3. See how?
Okay. Yeah.
Okay. So, what point do you think we're looking at?
Would it be 4 negative 11?
Yeah.
Okay.
In other words, the 2x makes that 2 a 4, and multiplying the 3 times the minus 3 brings you down to minus 9. Subtracting 2 from that brings you down to minus 11.
Okay, that makes sense.
All right, let's go on. Let's see, I should bring the next page up, I guess. And start at the top.
Okay.
Which do you think is our x-coordinate going to be 2 or minus 12? Because it's one or the other, right?
Yeah, I think it's minus 12.
Well,
Right.
If we take the minus 5 and we add 7 to it, we get 2.
But wouldn't it be a vertical shift?
But then, in other words, the only thing that's changing the x value is this part right here. This 2 there, the minus 2, remember that's going to change the y-coordinate. And this plus 3 is going to change the y-coordinates. But they're not going to change the x-coordinates. The only thing that changes the x-coordinate is this shift of 7 units. Is it left or right?
It's right. I mean, left.
It's left, so it's minus 12.
Yeah, that's what I was thinking.
Okay. And then, so our answer is either B or D. And the minus 2 does what to this 3?
Multiplies it, so it would be negative 6.
And then we have to add 3 to that.
So that would be negative 3. So it's D.
C. Okay. Those are a little tricky.
Yeah.
I don't come across those very often.
Yeah.
Problems,
I don't even remember doing
problems stated like that are unusual. Okay, so here we have a logarithmic equation. And you're allowed to use your calculator.
Yep.
To solve it. How do you use your calculator to solve this? What kind of calculator do you have? Is it a TI-84 or a Inspire?
It's an Inspire.
Okay. Conceptually, how would you use your calculator to solve this?
Would you graph like each of the sides
There you
of
go.
the intersection?
Wherever they intersect, that's the solution. Okay? And
that makes sense.
And that's exactly what I could do. If you like, I can do it on the TI-84, but this is y sub 1, this is y sub 2. Put them into your calculator exactly as you see them, and the Inspire will tell you if you've put it incorrect. It gives you that kind of feedback. And graph the two of them on the same page, and wherever their intersection point is the answer. Now, I noticed that their answers, this one gives you only an x, and everything else gives you an x and a y. Now, C and D don't give you y either. Notice the question, the solutions. Well, there's only an x here. There is no y.
Okay.
So we don't have a y value. So we can immediately rule out B and E. You notice there's no y up there. You're not going to have a y. You're going to have an x as your solution when you graph that.
Okay.
Let me do that on Wolfram Alpha real quick here. Let me think for a moment. Wolfram Alpha will actually solve it, so I better do it on my TI-84. Have you ever worked with one of these? The TI-84?
No, I've only ever worked with an Inspire before.
Okay, well, I'm in polar format here. I need to get in. I'm not sure it's necessarily worth the time for us to do this.
Yeah, I understand how to do it, so if you don't
As
want
long
to,
as
that's
you
okay.
know how to input that as y sub 1 and input this as y sub 2, or a second function, and graph them both at the same time, wherever they intersect will be x, the value of x.
Okay.
You probably only you know what? Let's go back. There could be two solutions here. It's possible that there's two different values of x that work. So we can't really rule off B. I was thinking that what they were giving us for B was the x-coordinate and the y-coordinate. Now I realize that's not what they mean. They mean there are two solutions for x. In other words, what if you graph this and you end up seeing this? There's going to be a solution there and another solution there. So it's possible you'll get two intersection points. So make sure when you graph it on a scale where you can see a possible second intersection point. But it looks like you only have to use, you'd only have to go out to -3 on the x in order to see both intersection points, if that's the answer. You'd have to go out to -4 on the x to see both intersection points if this is the answer. And if there's only one intersection point, go out to -4 on your x-axis when you set it up, the graph.
Okay.
You know how to do all that?
Yes.
Okay. All right. Let's look at 10. And the key really here for me was this right here. Choose the best answer using your calculator. Because we can solve that manually, but it's a bear to solve manually.
Right.
I'd have to exponentiate both sides, and then I got all kinds of difficult math there. But using your calculator, it's real easy. Just put that in as one function, that in as another. Find out.
Okay. I think I understand how to do 10 and 11, so I think I'm good on those.
So you're going to do 10 by graphing it and finding the local max.
Yeah, and we have like a setting where you can find the maxes and all of
You
that.
have kind of like a trace feature on there. Okay. Just make sure that there might be multiple local maxes. In other words, if you end up with a curve, this is a 5th degree polynomial, so it could have 4 loops in it. In other words, it could do 1, 2, 3, 4. It could be one local max, another local max, and then 2 local minimums. Okay? So when they say find the local maxes, plural, they might be talking about both of these 2 points, even though the second one is higher than this one. Because they haven't defined the parameters. The absolute maximum on this function is clearly when x goes to infinity, right? As x goes to infinity, y goes to infinity. So there is a local max somewhere, but there's no absolute max at all on the function. So clearly they're talking about a function that does look something like this, would have, incidentally, a 5th degree polynomial can only have 4 extrema. There's an extrema, there's an extrema, there's an extrema, there's an extrema. A parabola, a 2nd degree quadratic, can only have 1 extrema. Either up or down on a quadratic. So any polynomial can only have local extrema 1 less than the degree of the polynomial. But when they ask for where are your local maxes, that's a local max and so is that, even if this one is higher than this one. They're still both local maxes. A local max is basically defined mathematically as there are points. In other words, there is a point right there where points on either side are less. That's all it means. A local minimum means there is a point where on either side there are points above.
Okay.
So if I had a curve that looked like this, I got a ton of local mins and maxes. Every single one of these peaks, that's a local max, that's a local min. Local max and local min. All right, let's see. We were only supposed to go a half an hour. I've taken you too far here. But I don't want to leave you without knowing some of these. Let's see, we're going to meet again Wednesday night. You have to have this for tomorrow, or do you have to have this by Thursday?
It's all due on Thursday, so I think I'm good, and I understand most of the rest of it.
Finish the rest of it up on Wednesday, then.
Sounds awesome.
We don't have to do any more of this tonight. Okay, good.
Okay.
All right? Okay,
All right.
that's the way it works. Now, let me see. The only thing I don't think I have is your email address so that I can send you the link for finding this recording tomorrow.